When we work with motion in space, there are two particular kinds of uniform motion that we work with quite frequently. One is uniform straight line motion, and the other is uniform circular motion. When I have a straight line trajectory where the path traces a straight line in the direction of the vector r of t is equal to the components x sub 0 plus at, y sub 0 plus bt, and z sub 0 plus ct, there are no changes in the direction, which means my velocity, given by the components ABC, will be constant over the path of the trajectory, and the acceleration, a of t, will be the zero vector. We call motion associated with this kind of trajectory uniform straight line motion. And when I plot it, even in 3 dimensions, you can see that it forms a straight line with no changes in direction. If my trajectory forms a uniform circular path in a plane, it will be defined by a position vector r of t that points outward from the center of the circle. The direction of the motion and the linear velocity are constantly changing, but the magnitude of the vector r will be constant. The acceleration is always given by the vector a of t is equal to the negative of the vector r of t, and the first derivative of the position vector r prime of t, which is the linear velocity of the object, is orthogonal to both the acceleration vector and the position vector. We call the motion that's associated with this kind of trajectory uniform circular motion, and it traces out a path that forms a uniform circle of a fixed radius. My position vector for uniform circular motion is a two-dimensional vector with components a times cosine t and a times sine t. For a uniform circle in R2, the amplitudes have to be the same. The position vector is equal to the negative of the acceleration vector. This means that while my position vector points outward from the center of the circle, the acceleration vector points inward toward the center of the circle. And if I take the dot product of the position vector and the velocity vector, it will be 0 at all t, which means that my linear velocity is orthogonal to the acceleration vector and the position vector at all values of t. If I have a trajectory that's on a sphere, it will be defined by a vector in R3 that will have sinusoidal components. So the vector r of t, which is given by the components x of t, y of t, z of t, where x of t, y of t, and z of t have the form a times sine t or b times cosine t, and I have to have the magnitude of my position vector be constant. So let's work an example. I want to determine whether each trajectory lies on a circle in R2 or on a sphere in R3 centered at the origin. And if they do meet the criteria for one of these trajectories, I want to find the radius and show that the position vector and the velocity vector are orthogonal for all t. The first vector, r of t, is given by the components 3 sine t, 5 cosine t, 4 sine t, for the closed interval from 0 to 2 pi. The second vector, r of t, is given by the components 4 sine t, 2 cosine t, for the closed interval from 0 to 2 pi. In the first case, I have a three-dimensional vector, so I need to find out if this is going to be a trajectory that lies on a sphere in R3. The magnitude of my position vector is given by the square root of 9 sine squared t plus 25 cosine squared t plus 16 sine squared t. Rearranging a little bit and simplifying gives me a constant magnitude for my position vector of 5. This tells me that this is a trajectory that lies on a sphere in R3. It is centered at the origin and it has a radius of 5. The velocity r prime of t is given by the components 3 cosine t minus 5 sine t and 4 cosine t. The dot product of the position vector and the velocity vector is given by 9 sine t cosine t minus 25 cosine t sine t plus 16 sine t cosine t. This simplifies to 0 which tells me that my position vector and my velocity vector are orthogonal for all t. In the second vector, r of t is specified by two components, 4 sine t and 2 cosine t, on the closed interval from 0 to 2 pi. The magnitude of my position vector is given by the square root of 16 sine squared t plus 4 cosine squared t. This reduces to 2 times the square root of 4 sine squared t plus cosine squared t. This is not a constant magnitude, so this trajectory does not lie on a circle centered at the origin. So now you get to try it. Pause the video and determine if the trajectory lies on a circle in R2 or a sphere in R3 centered at the origin. If so, find the radius and show that the position vector and the velocity vector are orthogonal for all t. When you're ready, restart the video to check your understanding. The vector r of t is given by the components square root of 3 cosine t plus square root of 2 sine t, negative square root of 3 cosine t plus square root of 2 sine t, and square root of 2 sine t for the closed interval 0 to 2 pi. So I first want to determine if this is a trajectory that is either a circle in R2 or a sphere in R3. The vector has three components, so I need to determine if this is a uniform sphere in R3, centered at the origin. I need to find the magnitude of my position vector. I square each of my components and combine like terms, and I get the magnitude of my position vector is given by the square root of 6 times the quantity cosine squared t plus sine squared t, which reduces to the square root of 6. This is a constant magnitude, so this trajectory lies on a sphere in R3 centered at the origin with a radius of square root of 6. Now I need to show that the position vector and velocity vector are orthogonal for all t. I have my position vector, and my velocity vector, r prime of t, is given by the components negative square root of 3 sine t plus square root of 2 cosine t, square root of 3 sine t plus square root of 2 cosine t, and square root of 2 cosine t. The dot product of these two vectors is given by negative 3 sine t cosine t plus square root of 6 cosine squared t minus square root of 6 sine squared t plus 2 sine t cosine t plus the quantity negative 3 sine t cosine t plus square root of 6 cosine squared t minus square root of 6 sine squared t plus 2 sine t cosine t plus 2 sine t cosine t. I simplify this by combining all like terms, and I get a result that is 0. This means that my position vector and my velocity vector are in fact orthogonal for all t. This is how I can work with uniform circular motion in both 2 dimensions and 3 dimensions. Be sure and let me know if you have any questions.